Hello and welcome to Byjus Exam Prep. Welcome to another session in our knowledge series where we shall be talking about the heat budget of Earth. Now, when you hear about the term budget, what is the first thing that comes to your mind? Basically, when you think about budget, you think about a kind of a balance between things which are incoming and things which are going out. So, budget is something that you would have generally used in the term of the economic parlance under general circumstances. But when we attach this term with respect to the planet Earth in itself and we say heat budget of Earth, we basically refer to the energy balance. And that energy balance is always an interaction in between the amount of heat received by the planet on its surface and the amount of heat in turn lost by the planet from its own surface. So that balancing act, that is what we refer to as heat budget. So in this session, we shall be talking about more what this term actually means, what do we mean by heat budget, and what are the various different nuances regarding the incoming solar radiation, the outgoing terrestrial radiation, how is it that the surface of the planet maintains that energy balance. We shall also be taking a look at what are the various different factors which can oftentimes lead to slight disturbance in the heat budget here and there, and those are the factors which we refer to as climatic forcings. So without further ado, let us begin and let us understand the meaning of the term heat budget. Now here you have to understand that there is an equilibrium between the terrestrial radiation as well as the amount of solar insolation. Now, the energy radiation which is released, which is emitted from the sun, that energy is in the form of short wave radiation. And why is that? That is because sun as an object is very hot and has got a very high amount of energy. So as a result of that, when we talk about solar insolation in general, solar insolation is always carried out in the form of short wave radiation. These short wave radiations, they are very high in terms of energy level. Okay, so energy levels in this is very, very high. Then we also have what we refer to as the outgoing terrestrial radiation. Now, how is it that this terrestrial radiation is achieved? So just like any other object, after a prolonged day of heating, the surface of the planet also starts heating up. As the surface of the planet attains a certain amount of temperature, it starts acting as a hot object on its own. And any hot object will release energy in the form of waves, in the form of radiation. And because we are talking about the planet losing that heat, that is why it is referred to as terrestrial radiation. The terrestrial radiation which is released from the surface of the planet, that is always in the form of long waves. That is, it is low on energy level. The energy level here is comparatively low. Now, why is that? Why is it that the incoming solar radiation has got a short wave and has got a high energy level, whereas the outgoing radiation has got a long wave and significantly, when we talk about it, it has got a low energy level? That can be ascribed to the fact that when we talk about the planet in itself emitting radiation, the planet is much cooler as compared to the sun. So obviously the amount of energy released will always be much lesser as compared to the sun as well. Now this balance between the incoming solar radiation and the outgoing terrestrial radiation, that needs to be maintained, and that is very, very essential. Why is it essential? Because imagine a circumstance whereby the planet receives more amount of solar insolation and releases less amount of terrestrial radiation. In that case, what do we observe? In that case, over a period of time, you will observe that there is a surplus of heat, and the planet will start getting heated up quite consistently and quite at a rapid pace. The converse of it is also true. For example, let's suppose the incoming solar radiation is less and the amount of heat lost by the surface is significantly higher. that would lead to gradual cooling of the surface and the planet which will become much colder as a circumstance. Now, we know that the planet has maintained its temperature largely. There has not been a much deviation, a much change in temperature for that matter when we consider the surface of the planet. And that is because there is a kind of a maintenance of the energy balance, this energy budget. So when we talk about the heat budget, overall, we consider it in two components. One component will be that of the solar insolation, the other component will be that of the terrestrial radiation. And that is where we try to establish the balance between them. Here you have to understand that with the help of satellite data, satellite information, and also with the help of various different sounding rockets, etc., we have now got a detailed mapping regarding the amount of solar insolation received, absorbed, and reflected from the various different surfaces. That is how we are able to establish the circumstances in which this balance has been maintained. So when we talk about the incoming solar radiation, and when we take that as an example, here let me elaborate what do we mean by that. So here let us suppose that the incoming solar radiation or the incoming short wave solar radiation, so to say, let us suppose the total amount of it which falls on the top of atmosphere is taken to be 100 units, or simply put 100%, let us say. Now those 100 units of solar insolation which has received on the atmosphere, the top of the atmosphere, not all of it will fall on the surface. Some part of it will be distributed, dispersed within the atmosphere itself. Some part of it will be reflected back into the space from the atmosphere. Some part of it might be reflected back from the surface of the earth into the space. So there we get an idea that some amount of this solar radiation, not 100% exactly, but some amount of solar radiation or solar insolation is actually absorbed by the surface. And that is the unit, that is the quantum that we have to take note of. So here, let's say we take the total solar radiation or the total solar insolation to be around 100%. Out of that solar insolation, around 27 units are reflected upon hitting the cloud surface itself. Because if you take a look at the clouds in general, the clouds, while from the ground surface the clouds might appear to be very dark, blackish, grayish, etc. But whenever you take a picture of the clouds from top, they will always appear to be very bright and whitish in color. So these clouds, they re-reflect significant amount of this solar radiation. And as you can see, around 27 units are directly reflected back because of these clouds. Then, if you observe, then some amount of this solar insolation is absorbed by the atmosphere itself. Now we know that the atmosphere is composed of various different constituents. What are the various constituents of the atmosphere? You have the presence of gases, we do have the presence of water vapor, and we also come across the presence of dust particles. So together, all these three, they end up absorbing significant amount of this solar insolation. And that is also what leads to some amount of heating. For example, if you consider the regions of stratosphere, there we have the layer of ozone. We have what we refer to as ozonosphere. That ozonosphere in itself will end up absorbing some amount of ultraviolet rays and some amount of solar insolation in general, which leads to the heating of the stratosphere. So here around 14 units are absorbed in the atmosphere itself. None of these units, that is 27 which is reflected by the clouds, 14 which is absorbed by the atmosphere, none of these are utilized to heat up the surface. Then if you observe, some amount of these solar rays, they are scattered and distributed with the help of what? With the help of dust particles and other constituents of atmosphere. Thereby there is a scattering of light. That scattering of light not only gives us diffused light during nighttime and allows us to see even during pitch darkness. But also that works in the sense of trapping of heat. That is why heat is significantly greater closest to the surface. But even while that solar insolation is being scattered, some amount of that amount of insolation is re-radiated back into the space from the atmosphere itself. So you will observe around 6 units are re-radiated back into the space itself. Now these 6 units, that is what gives that brightish appearance to the atmosphere when you observe it from the outer space. When you observe the atmosphere from outer space, it will always give you a kind of a brightish hue, kind of something like that of a halo, not exactly a halo, but something like that. A brightish hue is what gives us the appearance of that, and that is because of these 6 units which are scattered into the space. Now after that, around 17 units, they do fall upon the surface, and these 17 units, they will heat up the surface. Now, the solar insolation will also reach the surface in areas where you don't have significant amount of cloud cover, or on average, you can say that around 34 units will reach up the Earth's surface directly without much of an interference. Even from hitting the Earth's surface, you will have 2 units of solar insolation which shall be reflected back into the space. And it is these 2 units which makes the Earth appear like a blue planet when again viewed from the outer space. So this figure around between 2 and 3, that is what is also referred to as the albedo of the planet. Now if you consider this mathematics, you will find that you have, when you consider the surface of the Earth, you have the absorption of 17 units, right, which are absorbed after being scattered into the atmosphere. After that, they reach and they hit the Earth's surface. And then you also have an additional 34 units, right, which reach the surface unhindered and they heat up the surface. So in total, if we have to calculate the amount of solar rays which reach and hit the Earth's surface and which carry on the process of heating of the Earth's surface, you come across a figure which comes out to be 51 units. So out of the 100 units which fell upon the top of the atmosphere, only around 51 units are utilized in heating up of the surface. We are not considering the heating of the atmosphere here, okay, because atmosphere has got its own independent heat budget. The surface has got its own independent heat budget. Here we are considering the budget of the surface. Now, the energy balance shall be maintained if all those 51 units are re-radiated back in the form of terrestrial radiation. So if we take a look at the long wave terrestrial radiation, that is the energy lost from the surface, we find out that energy is lost from the surface of the planet because of various different activities altogether. So what are those activities? What are those events which leads to the loss of energy? So basically, you have around 23 units which are directly lost from the surface as a result of the surface getting heated up and the surface acting as a hot body in itself. So let's suppose this is the planet. Now, when this gets heated up after a prolonged day of solar insolation, the temperature increases. As the temperature on the surface increases, it in itself starts acting as a hot body, and that is when you will have the long wave terrestrial radiation which is released. This turns out to be around 23 units. Why I am writing here negative is because this is the heat which is lost. Okay, heat gained is generally referred to as in a positive sense, and heat lost is referred to as in a negative sense. Now, we also know that once the surface of the planet gets heated up, the air above it also gets heated up. So some part of that heat is then transmitted into the air parcel immediately above it. as that air parcel gets heated up, that air parcel being lighter and being lesser in density will start rising up. As it ends up rising, what happens? It will transmit that heat from the surface in the upper layers of the atmosphere by a process which we refer to as convection. So convection is a significant measure or is a significant event which also helps the planet or the surface lose that additional amount of heat. This is the reason why, if you observe the equatorial areas across the globe, the equatorial regions, they will receive rainfall almost every day in the afternoon, in the evening time, because the heating which has happened throughout, that heating would have led to the convection process. That is how the surface cools, and that convection process forms very dense cumulonimbus clouds, and that leads to further climatic activities. So by this process of convection and various other methods of turbulence in the air mass, the vertical updraft of air, etc., the planet loses close to around -9 units. So you have further loss of 9 units which is experienced from the surface. And then again, by the process of evaporation and condensation in general, when you have evaporation which happens closer to the surface, all those water vapor particles, they get condensed eventually. That is also a methodology of transfer of heat from the surface higher up. So by that process, the planet manages to lose roughly around -19 units. Now here, please don't get confused regarding how do we get these numbers. How do we know it is 23, it is not 22, it is not 21, it is not 24. So as I told you before, this number, this data point is basically derived, is reached at after a host of different climatic experiments which have been conducted for a long period of time. And also nowadays, with the help of satellite data, we are able to map out the different temperature ranges across each and every micro units of the atmosphere, and we get a real-time information of the heat being lost from the surface or the surface being cooled down as a result of it. So that is how we get the number that we are talking about. Now, if you add up all these units by which the planet loses its heat, you will come across something or a number which is remarkable, and that is, if you add it up, you come across again 51 units. So overall, what have we observed is that the solar insolation, the incoming solar insolation, out of that, around 51 units, they reach the surface and they end up heating the surface. Now, when we have the surface in itself losing heat, that loss of heat can be achieved by various different events, various different phenomena. So one of those phenomena can be the process of convection and turbulence. One of those phenomena can be the process of evaporation and further condensation, and also one of that can be the direct terrestrial radiation. So overall, you can see that 51 units are also lost from the surface. What that means is that there is a kind of an energy balance which is maintained, and that energy balance is very important to maintain the temperature on the surface. If this energy balance is skewed, if it goes hayward, then you come across a scenario where the planet gets additionally heated up or the planet additionally cools down. Now, across the different parts of the planet, the rate of heating and cooling is never going to be the same, is not going to be the same. You will have different amounts of convection and condensation observed in the tropical regions as compared to maybe the higher latitude or mid latitudes for that matter. You will have more storm formations in the temperate or in the mid latitude region as compared to the equatorial area maybe. So that is why different parts of the planet, they have varying amount of these events and these phenomena taking place, leading to differential heat distribution in different parts of the planet. If we look at the overall heat balance and the heat distribution, we come across this very basic finding that around the region between 40° north and 40° south latitude, that is between 40° north to 40° south latitude, we generally come across a scenario where you have greater amount of solar radiation which is received, which is absorbed, and the terrestrial radiation which is released back is comparatively lesser in this region as compared to the solar insolation which is received. So in these areas, in between 40° north to 40° south, this is also an area which is referred to as the area of heat surplus. Okay? And beyond that, if we take a look at the areas beyond that, that is the higher latitude, obviously the amount of solar insolation which is received is significantly less. So as a result of that, we have these areas which suffer from a perpetual heat deficit. So in these areas, you have the planet losing larger amount of heat as compared to the amount of heat which is gained. So that is why the areas suffer from what we refer to as heat deficit. But then overall, it is not as if the equatorial areas or the tropical areas have continued to heat up throughout the history of the planet. Even the equatorial and the tropical areas, there we observe a maintenance of temperature, right? We have observed, for example, even if we take the example of our own country, we know that the heat is maintained at around, during the summer season, in the northern part you will experience the heat to be around 40°C. In the southern part, you will experience the temperature to be roughly around 30-35°C. So that temperature has been maintained. Yes, there are anomalies one year or the other, but overall the temperature is maintained. Why is it so? Even despite the fact that it is a heat surplus, why is it that the temperature is maintained? That is because of various different agents of heat distribution. And when we talk about heat distribution, that surplus amount of heat in a region that is carried over to the other areas of the planet with the help of various different agents, with the help of various different phenomena such as atmospheric circulation in the form of the permanent wind systems, right? You have permanent winds, then we have ocean currents. So all these events, they help distribute that heat from one region to the other. Having said that, sometimes that heat balance, that energy balance, that gets skewed and that gets disturbed for even a longer duration and even for a shorter duration. And that is because of events which we refer to as climate forcings. Now, these climate forcings overall are those events which lead to a prolonged, maybe excessive amount of heating or excessive amount of cooling which we observe on the surface. So these forcings overall can lead to a long-term rise in temperature or a long-term fall in temperature. This can be caused either by natural events or it can be caused by anthropogenic events or man-made factors as well. So what are those? So if we take a look at the natural factors which can disturb that energy balance, one can be the solar cycle and the solar brightness. The solar cycle over a period of 11 years, that undergoes a change, and that somehow can bring about a minor change in the amount of insolation. That brings about a minor change in the amount of insolation received. It can significantly increase the amount of insolation received, and whenever that happens, that will always disturb that energy balance. Then we also have the Milankovitch cycles, which was postulated by Milutin Milankovitch, whereby he talked about the fact that the planet Earth in itself, it changes its orbit from being completely circular to being elliptical over a long period of time. Even the axial tilt, that changes over a span of 41,000 years. Then the Earth as an object also wobbles around its axis and the axis takes a different direction every 21 to 26,000 years. So because of that, you have again a change in the heating and the cooling cycles. But again, this is a long-term phenomena. Okay, this is something which influences the heat budget on a long term. Then we have the volcanic eruptions. Whenever we come across a volcanic eruption, you have gases such as carbon dioxide, in certain cases carbon monoxide, and other gases which are immediately released, lot of water vapor. So that brings about a sudden heating. But at the same time, you also have gases such as sulfur dioxide, which escapes into the upper atmosphere, forms aerosols in the upper troposphere, and those brightish aerosols, they start reflecting the solar rays, bringing about a long-term cooling effect as well. So volcanic eruptions can bring about an additional heating or cooling, which is different from the natural energy balance that we have talked about. And also the man-made factor of pollution, whereby many of the times we release pollutants such as terrestrial ozone, such as carbon monoxide, carbon dioxide, methane, sulfur hexafluoride. All these pollutants are released, and also aerosols such as black carbon. When these are the effluents which are released, they significantly increase the rate of absorption of heat and thereby again have a possibility to change and disturb the energy balance of the planet. The recent spate of climate change that we are observing, the rise in temperature that we are observing, that is because of the anthropogenic factor of pollution, which is disturbing the heat budget of the planet. But even in that case, if you observe, the rise of temperature has not been exponential for that matter. The rise in temperature, when we set ourselves a goal for combating the climate change, what is the goal that we set? That by the year 2100, we have to limit the rise of temperature by 1.5 degrees. 1.5 degrees compared to what? Compared to pre-industrial age. That is almost 400 years back. So over that span of 400 years, we have to limit that rise by 1.5 degrees. It is a different matter altogether that even this 1.5 degrees can mean a significant and a drastic change in the climate around us, in the weather patterns around us, in the cycles of rainfall and drought around us, something that we are already experiencing and we have begun to experience in our country, and especially in parts of the country such as northeastern states, which have been receiving increasing bouts of concentrated rainfall, which is leading to floods and destruction. So that is all that you need to know about the heat budget, the factors regarding heat surplus and heat deficit, and thereby the heat distribution. And we have also looked at what are the events which can end up disturbing this heat budget. Now let us pick up a few questions. Shahid Hussain, why they are called short waves? That is because the wavelength is particularly short because the energy level is very, very high. Heat budget is good or bad for humans? So in this, I would say that heat budget overall, if it is maintained, it is always good for us because that won't lead to any significant temperature rise or a temperature deficit. Difference between conduction, convection and advection. So when we say conduction, there the transfer of heat takes place between materials which are in direct contact with each other. When we say convection, here the transfer of heat takes place by movement of particles, as we observe in the atmosphere, as we observe in liquid surfaces as well. And when we talk about advection, it is again the distribution and transfer of heat which is experienced due to the horizontal movement of air masses. In a nutshell, can we conclude that balance between the incoming and outgoing heat is referred to as heat budget? Yes, you can say that. You generally get a mains type of question being asked from here in the examination, and that is why it becomes important, because there you have to count out these units which are gained and the units which are lost. Uh, why is the day temperature maximum in May and why not after the summer solstice? That is because by the time that the summer solstice occurs, we in India particularly, we also end up experiencing the other interventions in the form of rainfall which lower the temperature. Whereas in the month of May, you don't have that incidence of rainfall. That is why the heating is quite continuous. Terrestrial radiation is basically the heat which is lost from the surface. The word terrestrial associates with the planet in itself. So, after a prolonged heating, the planet will also get heated up. And any hot object, any hot body for that matter, will release heat from the surface into the atmosphere. So, that is terrestrial radiation. Other planets also reflect heat? Absolutely yes. The other planets, they reflect so much of heat, that is why, and they don't have an atmosphere to trap that heat. That is why we come across a scenario whereby the day temperature is very, very high, but the night temperature is extremely low because all the heat is lost. And this is generally done by the terrestrial planets, not the gas giants. So we are talking about the planets of Mercury, Venus, Earth, and Mars. Okay? So, that is all the questions that we shall be taking up for today. Now, one of the other question that I will take up is why the name climatic forcings. So, the name climate forcings is because these are the events which unfold a spate of change in temperature, rise in temperature, or fall in temperature. That is why it is climate forcings. What is Milankovitch cycle? So, Milankovitch cycle, these are the cycles which were postulated by Milutin Milankovitch, which talks about the prolonged heating and cooling of the planet, and that is what causes ice ages and glacial ages on the planet. So, Milankovitch talked about the fact that when we have the planet rotating around the sun, moving around the sun, yes, there is a gravitational influence of the sun, but time and again, the Earth is also influenced by the gravitational attraction of Jupiter and Saturn. These are very giant planets. So, as a result of that, the Earth's orbital plane, it varies between being completely elliptical to being somewhat circular. And that is what changes the amount of insolation in the long run. Also, the planet on its axis, the tilt that the planet has on its axis, that tilt changes owing to the gravitational pull of attraction, because we know that the Earth as a planet is not a perfect sphere. It is a geoid which is bulged around the region of equator. So, that is why you have a kind of a change in axis. So, the axis changes between 21.5 degrees to almost around 24.5 degrees, but generally we take it between 22 to 24.5 degrees. Okay. Then aerosols in upper troposphere release which thing? They don't release anything, they reflect the solar rays, the aerosols which are present. Not all aerosols, few of the aerosols. Does this differential heating system account for the 4 o'clock showers in the equatorial zone and also the formation of La Nina? So, yes, some part of that differential heating, that is what leads to the creation of ITCZ after all, which drives all these permanent wind systems. But then eventually the La Nina, the El Nino cycles, they are because of solar insolation and normal heating additionally attached with the permanent wind system. Are there any artificial methods or techniques to maintain the heat budget? Yes, there have been certain methodologies which have been talked about, but then not much work has been done about it, not much research is being carried out, because you need to enforce them on a very large scale, on the scale of a large planet. So there are talks about creation of artificial mirrors, and those mirrors can reflect the solar rays, thereby cooling the surface. But then you cannot have that across a large area, and we don't know what the outcome of that will be. So that is why it is not being implemented. Okay? So that is all That will be there for the session, and we meet again on Monday, where we shall be talking about the factor regarding interior of the Earth. Thank you.